Today with us is Thomas Wehr from Friedrich-Alexander-Universität in Erlangen-Nürnberg. And Thomas is pursuing his PhD at the Chair of Technical Information Systems since March 2024. And actually, the chair's research projects involve Web of Things in different ways, where we have actually seen them handling baggages at the Munich airport in Meetup 17 from a colleague of Thomas. They also developed an Android health app to interact with wearables described by TDs or extending TDs with preconditions and so on to enable planning. And in the broader sense, the chair's research is around the semantic web, linked data, knowledge graphs, sometimes going towards the data spaces, and there they work also together with the data space and Internet of Things Solutions department at the Fraunhofer Institute for Integrated Circuits. And with this, we can go towards the presentation. So later on, when you're asking questions, just quickly introduce yourself. And yeah, so with this, Thomas, you have the floor.
Yes, hello. As Ige said, my name is Thomas Wehr, and today I'll present to you a tool we developed at our chair for visually creating WoT consumers. I'll start my presentation with a brief motivation for this tool. Next, I got a short slide on visual programming, in case anyone here hasn't heard the term before. Then I'll show our tool called BLAST for block applications for things and present some of its features along with examples. Then I'll explain how BLAST dynamically generates new blocks for devices added during runtime. And afterwards, I'll give you a quick demo of BLAST. And lastly, well, I'll just summarize everything again. So when we started developing BLAST, we just had a handful of Bluetooth and HID devices and wanted to write programs for them quickly. So we wanted to create a programming environment, but with some requirements. First of all, it should be portable, meaning it should be usable on as many devices as possible, which is why we decided to make it browser-based. Additionally, we wanted this environment to be as accessible as possible. So people without programming experience should be able to create programs to interact with IoT devices. So we decided to make it a visual programming environment. And in a minute, I'll explain more about visual programming. But first, our next requirement, which was that we wanted to be able to add new devices without changing any code of the environment. Well, and I guess all of you know the solution to that. We use the Web of Things, enabling us to add new devices by simply parsing its thing description. And then lastly, we needed support for Bluetooth and HID devices, which is why we developed custom protocol bindings. Now, as promised, a quick slide on visual programming to make sure everyone knows what we mean by this term. So visual programming in general refers to a programming environment where you arrange graphical elements to create programs instead of creating them textually. Now, there's many types of many different types of visual programming, like flowcharts or node graphs. You might have seen Node-RED before, which is also considered visual programming, and it has a WoT integration. Then there's state machines, data flow programming, and many more. But in BLAST, we decided to employ block-based programming. In block-based programming, you just snap predefined blocks which represent program constructs together like puzzle pieces to create programs. Block-based programming is very popular in education. It's used to teach children how to program. For example, when we presented BLAST at a fair last year, we had a lot of children coming up to our stand and say, oh, I know that it looks just like Scratch, and they were able to create programs without any instructions. So I think it's fair to say that block-based programming is very intuitive and easy to use. In Blast animation, you arrange matching blocks together to build programs, and compatible pieces will just snap together, whereas incompatible pieces won't. Therefore, you cannot make any syntax errors if the visual programming environment is implemented correctly, of course. Now, let's look at how we use visual programming with the Web of Things. Our tool called BLAST, an acronym for Block Applications for Things, is built on Blockly, NPM library by Google for building block-based visual programming environments, and Node.WoT. And in BLAST, you have a browser-based visual programming environment for creating WoT consumers and for executing them. To do so, BLAST offers a number of predefined blocks. For example, to define program control flow, like loops or if statements. Just looking at this example down here, you can see we read a possible drinks property of a coffee machine, which returns an array or a list. And BLAST has a predefined block for iterating over array elements. So in here, we iterate over the return value. And if one of the elements is equal to espresso, we can output a text message saying espresso is available. Additionally, BLAST provides a couple of blocks for string operations like text input and text output and many common string operations. Using those, we can extend this previous example and prompt the user to ask which string he would like to bring, and then later on use the provided value when iterating over this returned array. Also, there's a lot more predefined blocks, way too many to show you examples for all of them. But to name a few, BLAST includes common mathematical operations, HTTP requests, text-to-speech, speech-to-text, function definitions, function calls, blocks for handling objects, and many more. So, for example, we can execute an HTTP request via BLAST and then pass the returned text as a JSON, or to receive an object, then access a specific property of this object, convert it to a number, and lastly perform math operations on this number and output the result. Now this is a very interesting feature because you don't see it very often in textual programming languages, or at least not as accessible as here. BLAST has an own event loop and allows to define custom states and triggers for when BLAST enters or exits a defined state. For example, this is a very simple example. This block down here defines a state called even, and with the condition that a variable number modulo 2 is 0, so the number is even. Now this block here says whenever my variable is even, so BLAST enters this state, this given condition is true, then I want to output a text, and up here we can see that we increment this number from 1 to 10, and well, on the right side you can see the output of this program. So whenever the number is even, we output a text. This is a feature we often use when polling sensor values, for example, if the sensor device does not offer own event notifications, then this comes in very handy because you can define own events using this. Now, the cool feature WoT allows us to do is adding new devices without changing any code. BLAST only needs to consume a thing description of the device and can generate custom blocks for the device's interaction affordances. Let me show you what that looks like. So if the thing description contains readable properties, then BLAST generates a read property block with a dropdown listing all the readable properties. And of course, BLAST does the same for all writable properties. So here you have a write property block listing all writable properties. Additionally, BLAST parses the provided data schema for all inputs and outputs to make sure only blocks of the correct data type can be attached to the generated blocks. For example, if you think about the possible drinks property I showed earlier, which returned an array, then you won't be able to directly perform string operations on it because it's an array and not a string. BLAST also passes the properties description to display a hover text when the user moves this cursor up. And very similarly, BLAST creates blocks for events, for actions, sorry, and BLAST passes the input and output type to eliminate syntax error, and the actions description again to pass a hover text. What's very similar, we create event blocks, but this one looks a little different because in event blocks, you cannot just place input and output blocks, but you can attach statements. So an event needs an event handler to do something when the event is emitted. So right here, you can see that if the coffee machine, for example, emits an out of resource event, then this block will execute every block's placed in here. So in this example, we would display a text saying coffee machine is out of resources, and then the return string of the out of resource event. But of course, you can also place, for example, an invoke refill action event in here to refill the coffee machine whenever it's out of resources. Then, as I said, BLAST is built on Node WoT, which did almost everything we needed out of the box. But there was two things we had to adapt. We needed to support Bluetooth and HID devices, so we built our own protocol bindings for these. Since BLAST is primarily used within the web browser, the protocol bindings we use use the W3C Web Bluetooth and Web HID APIs, but we also have a node adapter for both of them, which use popular NPM packages called BLE host and node HID. And the second modification or extension we had to do was we extended the TET stream codec, because we have a lot of devices that communicate with byte streams, and to simplify the usage, we added two more JSON schema keywords, namely scale and default, and I got examples for these on my next two slides. So for example, the scale keyword we needed for a device called RubyTech. This is a small sensor device which broadcasts measurements over Bluetooth every couple 100 milliseconds, like temperature, humidity, pressure, and acceleration, and so on. And well, these measurement values are all sent in one big byte string. And yes, the RubyTech documentation explains which measurement starts at what offset and gives the measurement length, data type, unit, and so on. And in this documentation, we can see that, for example, the humidity measurement is broadcast in 0.0025%. Therefore, to get a meaningful result, our WoT consumer would have to multiply the transmitted value with a scale factor first. Now, instead of including this multiplication in every program that reads the RubyText humidity measurement, we wanted to describe this in its thing description. So we added a scale keyword and extended the octet stream codec to do this multiplication for us. Next, I got an example for the default usage. Very similarly, we added a default keyword to the octet stream codec because another device we have which controls colored LED lights, also accessible via Bluetooth, communicates with byte strings too. And in this case, this byte string contains a lot of bytes that don't change for the same operation, but have to be included, like bytes indicating the command start, command length, and so on. So with a default keyword, the user does not need to know these bytes, or whoever uses a write property operation. You can just say we can just set command start, for example, to 126 by default, or command length to 7, and so on. Because these commands just indicate, or these bytes just indicate what commands we're going to use. Then there is 3 values the user has to provide, namely the red, green, and blue value the LED should be set to. And afterwards, again, there's some fixed bytes that we can set by default. Now, using this default keyword, we don't have to pass all of these values anymore when writing a color property, but instead we can just write property color with only providing red, green, and blue values. Now, enough theory, let's see Blast in action. So when you open Blast, this is what you see. You have a workspace in the middle for placing blocks in, and a couple of block categories on the left side. Now, a very basic Hello World program could look like this. You can execute programs up here. So this one just outputs Hello World. Then we have some predefined programs, for example, the one you've seen when I talked about how you can define states and events in Blast. So this one has a predefined state for when number is even and when number is odd, and outputs texts whenever one of these states get entered. So if I execute this, well, as you would expect, you see outputs for whenever number is set to an odd or even value. But I think more interesting are programs or devices. So today I have one device called Stream Deck. This is a small device with 6 buttons. So connecting this, we should be able to listen to button events. And last, I can connect to Bluetooth and HID devices, and the Stream Deck is already pre-configured, so I can just select it in here. Give it a name, let's call it SD for Stream Deck. Then Blast generates a new block representing the device or the exposed thing in WoT terms. And in case of the Stream Deck, I get some blocks for writing a color property or writing numbers, strings, booleans on the display. And of course, an event block, which listens to button presses of the Stream Deck. So the demo I thought of was we have the Stream Deck and the second device, Bluetooth-controlled light bulb, the Govi light bulb. Let's connect this one too, and then we control this light bulb via, need to turn it on first, via the Stream Deck. The light bulb right here, let's name it lamp. This created property blocks for the lamp. So now I can control the lamp's power, for example. I can set the lamp's color to any of these values, or create my own color value with a color block. But let's not overcomplicate things here and say, whenever I say press the first button, so whenever button 1 is true, button 1 true, color should be set to red. If I click another button, say button 2, button 3, you can just copy paste blocks. So let's make button 2 set the lamp to yellow, and button 3, set the lamp to green, so we can have our own little traffic light right here. Let's execute this program, see if it works. If I press button 3, the lamp turns green, button 2 makes it red, yellow, the first button red. Yes, of course, you can extend this program with all of these different blocks in here. Like, as I said, we have loops for control structures. We have Sparkle queries to query RDF data. You can send HTTP requests and so on. I guess it makes most sense if you just try it out yourself. It's fairly easy to use, as I said. Yes, with that, let me just quickly summarize what I showed you. Turn off the slide real quick. Okay, so I presented BLAST, a visual programming and execution environment for WoT Consumers, which provides some predefined blocks for basic programming constructs and for some devices, but it's also BLAST is also able to consume thing descriptions to generate blocks for new devices. It has its own event loop for defining states and state transitions, and we also implemented custom protocol bindings and extended the octet stream codec to handle the JSON schema keywords, scale, and default. You can find BLAST on GitHub at github.com/wintechies/blast. And yes, that's my presentation. Thanks for your attention. On this slide, you can find my contact information, but I'm also on the WoT Discord server if you prefer that.